Hi everyone, I'm Shunyu Wang from University of Virginia, and first I want to thank the organizers for invitations. So in these two talks, I want to tell you something about the naturality of Lagrangian loss invariant under positive contact surgery and its applications. In the first talk, I will go over the background of the contact geometry part and try to tell you what those words means. And the second talk, I want to talk about the applications, which mainly I want to convince you that these two Lagrangian knot are not Lagrangian isotopic. So the background, I will mainly focus on the contact geometry part and how we got the Higgs flow invariant from the contact geometry. So I will first talk about the open book, contact invariant, Lagrangian knot, and the loss invariance, and finally a little bit on the contact surgery. So let's start with the definition of the contact three-manifold. So a contact three-manifold YKC is a three-manifold Y together with a two-plane field distributions KC, such as for any one form alpha with kernel of alpha equal to KC, you have alpha which d alpha is positive. So in left corner, you can see that it's a R3 with KC standard, where KC standard is equal to the kernel of dz minus y dx. And you can see all of those plane field. Another way to interpret the contact structure is that for any surfaces in YKC, the tangent space of the surface is never gonna equal to the like the tangent plane. Okay, so next I want to talk about the open book. So an abstract open book or just an open book is a pair P phi where P is an oriented compact surfaces with boundaries, and phi is a diffeomorphism satisfy that phi is identity in the neighborhood of the boundaries, and we often call phi the monodromy of the open book. And the P, we call it the page of the open book, and the boundary of P, the binding of the open book. To give an abstract open book, we can construct a three-manifold associated to its open book as follows. So this M of phi is a three-manifold, and it's equal to P phi, gluing along those solid torus, where P phi is a mapping torus of the page P and with the monodromy. So this is a picture of the P phi. So in other words, we first take the P cross with the interval I, and we glue the top and bottom P0 and P1 by the monodromy phi. Okay, then this P phi is a manifold with boundary, and the boundary are bunch of torus. So in other words, bunch of these bindings. So S1 cross this monodromy, like this green circle. And the gluing map it's given by you glue the longitude of the solid torus to the bindings and glue the meridians of the solid torus. The one bounds the disk to the S1, like the I part, the interval part. Okay. So that's how we construct a three-manifold with an open book. And we can assume that for any closed three-manifold, there's also an abstract open book associated with that. Okay, so how that's related to the contact geometries? So it's a theorem given by Giroux. For any closed-oriented manifold, there is a one-to-one correspondence between the oriented contact structure on M and the open book decomposition of M. And here it's a brief description. So if I have a YKC, the open book P phi is kind of compatible with YKC in the following sense. The first, the three-manifold we construct in the above, so M of phi is equal to the three-manifold Y. Moreover, the tangent plane KC is transverse to a neighborhood of the bindings transfer to the neighborhood of the boundary of P, and tangent to the rest of P everywhere else. So we can see these picture descriptions. So using this open book, we can kind of construct like a contact invariant in the here flow. And here's the idea. So the contact invariant, we want to associate contact structure y_c to an invariant leaving the actual head of -y. And we'll see why we want the -y in a second. And so the idea is to associate the open book like compatible with this contact structure to an intersection point in the Higgs diagram. Okay, so in other words, we want to associate P phi to a diagram, a Higgs diagram, sigma beta alpha W describe -y, and like a point in T alpha intersect T beta such as the Higgs flow differential is equal to 0. Okay, so here is how we construct the Higgs diagram. The first, the sigmas is given by P0 union minus P1, where this minus is just the reverse orientations. So it's just like the surface given by gluing two pages along their binding. Okay, so what about the alpha and beta curves? So for the alpha beta curves, we first pick a basis AI for the page P0s. Here is an example of like the one with 3 boundary components. So the basis means that if we cut along these curves, we get a disk. So we have this A1, A2s, and so alpha curve is just we have another like corresponding AI bars in the minus P1 pages, and we just glue them together. We just like so to form like a alpha curves. So the alpha I is just AI union AI bar. So what about the beta is? The beta is are coming from these BIs, where the BIs are just the parallel push-offs of each AIs, such as BI intersects AI transversely at one point. But on the other side, on the minus P1 side, we're not just using the identity BI bar, but instead we put the monodromy on that. So in here, instead of we put B1 bars, we will put phi of B1 bars. We are using the monodromy. And similarly for other BI. So the betas are BI union phi BI bar. And after we put it together, it will give us a Higgs diagram. And it's not that hard to check. The sigma beta alpha, it's the Higgs diagram to -y. And finally, we put the base point outside the like the AI BI strip. So it's in here. Then also it's not hard to check if we let xi equal to AI union intersect BIs and x is all those intersection points, you can see that this x is actually a cycles. And it's like if you want something live inside the boundary of xi, it has to hit this base point, so which is not allowed, so it's a cycle. And we just define the homology class of that one to be the contact invariant. Okay, so that's all for the three-dimensional part. Next, I want to move on to the Legendre part. So a Legendre knot in a three-dimensional y_c is an embedded S1 such that it's always tangent to the c. So in other words, its tangent space it's lie on the tangent plane. So in R3, there's very good diagrammatic way to describe that. It's given by front projections. The front projection is from R3 to a projection from R3 to R2, and it's given by XYZ to XZ plane. And the diagram of that satisfies these three properties, so there's no vertical tangencies, and the only non-smooth points are those cusps. And at each crossing, the slope of the overcrossing is always smaller than the undercrossing. Here are several examples. of these two are Lagrangian unknot, and this is a Lagrangian right-hand triangle, this is a Lagrangian left-hand triangle. Okay, so similar to a smooth case, there are like randomized moves for the Lagrangian knot. So two front diagrams represent the Lagrangian isotopic knots if and only if they are related by the regular homotopy, so like the homotopy that's not involved like crossings, and a sequence of Lagrangian randomized moves. And this is 3 Lagrangian randomized moves, and you need more like the one like rotated 180 degrees about coordinates. So for example, there's one like where this cup is like in the below. Here's the example of this Lagrangian randomized moves. So the first one, I can pull this cusp like unders using Lagrangian randomized 2 moves, like which is like 180-degree rotations of this diagram. Then I can use the Lagrangian randomized 1 move to kill this top hat, and it becomes this. So these two Lagrangian unknot are Lagrangian isotopic. So in general, it's really, really hard to see if two Lagrangian diagrams are related by Lagrangian randomized move. For example, you can try to using this Lagrangian randomized move to show these two Lagrangian figure eights are actually Lagrangian isotopic. Okay, so if you are curious the step, you can check with me in the discussion. It took me an hour to figure that out. Okay, so since it's really hard for the Lagrangian randomized move, we better have some kind of invariant for Lagrangian knot in terms of the front projections. Oh, by the way, these are only works for the knot in R3 with standard context structure. So the two classical invariants are, firstly, the certain banking numbers. The TB is given by the rise of the front projection minus a half of number of cusps, and the rotation is given by half of number of downward cusps minus number of upward cusps. For example, this first one, first unknot, it has rise equal to 0s, and it has 2 cusps, so the TB is -1, and it has 1 under, 1 upper cusp, so the rotation is 0. But in the second one, we can see that the rise, so this is a negative crossing, so the rise is -1 and minus a half times 2 cusps, so it's -2. And the rotation number, this is upward, and this is also upward, so the rotation number is -1. So even these two are smoothly the same thing, so they're smoothly just unknot, but because they have different TB and different rotations, so these two Lagrangian unknot are not Lagrangian isotopic. And the third one is just another example of check. You can check it has TB equal to 1 and rotation could be 0. Okay, so there is an operation to the Lagrangian knot called the stabilizations. So if you have your oriented knots have a part looks like this, then you can do these two kind of stabilizations. One is called the positive stabilizations and negative stabilizations. So the positive stabilizations is you add 2 downward cusps, and the negative stabilizations is add 2 like upward cusps. And similarly for the other orientations. And the right hand side is just examples for the how you do stabilization for the Lagrangian unknot. So in general, if you have a knot after you do a positive stabilizations, the TB of the positive stabilizations is 1 less than the original one, and the rotation of the positive stabilizations is 1 bigger than the original one. However, if you do a negative stabilizations, the TB is still 1 less, but the rotation is also 1 less. Okay, so now let's see how we can relate it Higger floor, or more precisely, the knot floor to the Legendre knot. Okay, so this is called the loss invariant. So similar to the contact invariant, in these situations, we want to associate the YC and the Legendre knot L inside YC to an element which we call the loss invariant L of L inside the knot floor of the minus Y and L. Here you should think the L is the smooth knot type. And the idea is very similar. So instead of we want to relate it just P phi, we want related the P phi and L. In here it's the Legendre knot L, such as it lies on the page of the P. Remember we said that on the page of the P, we can, like, the contact plane is tangent everywhere to the P except in the neighborhood of the bindings. So their theorem says we can always find the open book such as the Legendre knot L is lying on the page. We want to associate these triples to a doubly pointed Higger diagram, sigma, beta, alpha, z, and w, that correspond to the knot L inside the manifold minus Y. And again, element X in T beta intersect T alpha, and such as the differential is equal to 0. Okay. So the procedure is basically the same thing as a contact invariant, but in here you just need to be careful when you choose your basis for the for the page, right? So you want your A1 only intersects your Legendre knot L at one point. And then if you take the parallel copy of the A1, your B1s, and you put the Z between the strip and W's outside the strip, and you can see that in the Higger diagram, this W and Z is exactly describe your Legendre knot, smoothly describe your knot L. Okay, then by the similar argument, you can see that the X is a cycle in CF hat of minus Y, it should be minus YL, and we call the homology of that it's a loss invariant of L. Okay, that's how we associate a Legendre knot Higger flow invariant or knot flow invariant. Okay, so last I want to talk a little bit about the contact surgeries. So in here, if I just call a different name, if S is a Legendre knot in YC with smooth knot K, then the N contact surgery on S, which is smoothly an N plus TB of L surgery on K. And after we do that contact surgery, the result is another contact manifold. So here is like schematic pictures. So if we have a YC and Legendre knot S inside YC, if we do a contact plus N surgery on S, it will give you another contact manifold, which is called Y of N of S, and with contact structure C of N of S. And similarly, if you think a Legendre knot is like inside YC, which is disjoint from S, there is also a map from YC and the Legendre knot to Yn of S, C of S, and another Legendre knot L of S inside this contact manifold. Then one can ask, doing this map, is the contact invariant of YC map to the contact invariant of YNS, C, and S, and is a loss invariant of L map to the loss invariant of L of S. And the first answer is yes, and the second answer is the theorem of the next talk. Thanks for listening. See you in the part 2.